Life on Earth may not have begun here at all. Long before oceans or humans existed, tiny seeds of life could have drifted through space, sheltered inside comets, asteroids, or dust, waiting for the right conditions to spark life. If true, every organism on Earth carries a story that began far beyond our planet, hinting at a universe where life is older and more interconnected than we imagine. Panspermia is a hypothesis that pushes the boundaries of how we understand the origin of life, suggesting that life on Earth may not have been born here at all, but instead arrived from somewhere else in the cosmos. The term itself comes from the Greek words pan, meaning all, and sperma, meaning seed, evoking the image of life being scattered like seeds across the universe. At its core, the theory proposes that microscopic life forms, or even complex organic molecules capable of forming life, could have existed elsewhere in the galaxy or beyond, surviving the vast, inhospitable distances of space before eventually landing on a hospitable world, our Earth. This concept radically redefines our perspective on the origins of life. Traditionally, science has focused on abiogenesis, the process by which life arises from non-living chemical compounds under specific environmental conditions on a planet. But panspermia suggests that life might be much older than Earth itself, carried across interstellar or interplanetary distances and deposited here as if by cosmic gardeners. Life, in this view, is not an isolated phenomenon, but potentially a universal one, capable of spreading from one world to another. Importantly, panspermia doesn't claim to explain how life began in the first place. It only proposes a mechanism for how it could travel and propagate across the cosmos. This subtle distinction opens up mind-bending possibilities. Life on Earth might share its roots with life elsewhere, and Earth could simply be one node in a much larger cosmic network of living systems. By framing life as a cosmic phenomenon rather than an earthbound accident, panspermia challenges our notions of uniqueness and invites us to think of life as a potentially universal legacy. Panspermia can be divided into two main forms: natural panspermia and directed panspermia, each offering a distinct perspective on how life might have reached Earth. Natural panspermia envisions life spreading across the cosmos through purely physical and natural processes. Tiny microorganisms or organic molecules could hitch rides on comets, asteroids, meteoroids, or even interstellar dust, surviving long journeys through space until they eventually land on a suitable planet. Events such as asteroid impacts could blast rocks containing microscopic life off one planet, sending them hurtling through space and eventually delivering life to another world, a process known as lithopanspermia. In this scenario, life is dispersed by chance, governed by the laws of physics and the randomness of cosmic collisions. Directed panspermia, on the other hand, is a far more provocative concept. It suggests that life could have been intentionally spread by advanced intelligent civilizations. In this scenario, extraterrestrial beings, aware of the fragility and potential of life, might deliberately send microorganisms or genetic material to other planets to seed life, essentially acting as cosmic gardeners. This theory raises profound philosophical and ethical questions. Could life on Earth be the result of a deliberate experiment by an ancient civilization? Are we part of a cosmic plan rather than a random accident? While speculative, directed panspermia has been seriously considered by some scientists because it provides a plausible explanation for life's rapid emergence on Earth and the remarkable similarities shared across all known organisms. Both natural and directed panspermia underscore the idea that life might not be unique to Earth, but rather a cosmic phenomenon with origins and potential connections far beyond our planet. They suggest a universe in which the seeds of life are not confined to one world, and where the story of existence might be far older and more interconnected than we have ever imagined. At the heart of the panspermia hypothesis lies the concept of the seeds of life, tiny, hardy microorganisms capable of surviving the extreme conditions of space and eventually giving rise to life on a new world. These microorganisms are not fragile. Many belong to a category of life called extremophiles, organisms that thrive in environments previously thought inhospitable. On Earth, we find extremophiles surviving boiling hydrothermal vents, frozen tundras, acidic hot springs, and the crushing pressure of the deep ocean. Such resilience makes it conceivable that they could endure the harshness of outer space, provided they are shielded in protective niches like the icy cores of comets or the interior of rocks ejected from planets during collisions. Comets, composed largely of ice and dust, could act as natural freezers, preserving microbial life in a dormant state for millions of years. Similarly, microorganisms embedded within the interior of an asteroid or meteoroid would be protected from lethal cosmic radiation and the vacuum of space. In these conditions, metabolic activity could nearly halt, allowing the organisms to survive incredible spans of time until they encounter a suitable environment where life can flourish. Laboratory experiments have even shown that certain bacteria can survive prolonged exposure to space-like conditions, reinforcing the plausibility of this mechanism. The concept of these seeds of life expands our understanding of how life might travel vast cosmic distances. Rather than requiring ideal conditions at every step, these hardy organisms could endure long journeys, lying dormant in frozen or rocky vessels until a chance collision or atmospheric entry delivers them to a planet where they can awaken and proliferate. In essence, life could be packaged, preserved, and transported across the galaxy, waiting for the perfect moment to take root. The universe provides a variety of natural mechanisms capable of transporting life across vast distances, forming what can be thought of as cosmic delivery systems. One of the most prominent of these are meteors and asteroids. When a massive impact occurs on a planet, rocks can be ejected into space with enough velocity to escape the planet's gravity, carrying within them microorganisms or organic compounds. These rocks can drift through space for thousands or even millions of years before encountering another planetary body, potentially delivering the seeds of life intact. This process, called lithopanspermia, demonstrates how life could leap from one world to another without ever evolving independently on the recipient planet. Comets serve as another vital delivery system. Rich in water ice, organic molecules, and dust, comets can carry dormant microorganisms, shielding them from the intense radiation of space. As a comet approaches a star, heating can release these materials, seeding nearby planets, or even delivering water and organic compounds that provide the foundation for life. Interstellar dust, tiny grains of carbon-rich material spread throughout the galaxy, could also act as carriers for simpler life forms or prebiotic molecules, creating a subtle but widespread mechanism for distributing life. Planetary ejecta, created when meteorite impacts blast debris into space, is particularly intriguing. Even Earth itself may have sent rocky fragments to the Moon, Mars, or Venus, while receiving material from these neighboring planets in return. These processes are not just theoretical. Scientists have discovered meteorites from Mars on Earth, demonstrating that material can travel between planets naturally. In all these mechanisms, space acts as both the highway and the test chamber for life, subjecting microorganisms to radiation, vacuum, and extreme temperatures, yet allowing them to endure long enough to reach hospitable worlds. Through these cosmic delivery systems, the panspermia hypothesis paints a picture of life as something not confined to a single planet, but as a phenomenon that can traverse the universe, carried on rocks, ice, and dust, connecting worlds in ways humanity is only beginning to comprehend. Lithopanspermia is one of the most fascinating and physically plausible mechanisms proposed for the spread of life across planets, and it centers on the simple yet profound idea that rocks ejected from a planetary surface during impacts can act as vehicles for life. Consider a massive asteroid or comet striking a planet at high velocity. The energy released is enormous, enough to vaporize portions of the surface, generate shock waves, and literally blast fragments of rock into space. Among these fragments, some could be of sufficient size and density to shield any microbial life or prebiotic molecules embedded within them from the deadly extremes of space: vacuum, freezing temperatures, and intense cosmic radiation. This natural rock shuttle could then drift through space for thousands, even millions of years, potentially crossing the gravitational boundaries of solar systems before being captured by another planet's gravity and ultimately impacting its surface. The survival of life during this process hinges on a combination of physical shielding and biological resilience. Laboratory experiments simulating the conditions of space have shown that certain extremophiles, microbes that can survive intense radiation, desiccation, and extreme temperature fluctuations, are capable of enduring the stresses of space travel. For instance, some bacteria can enter a state of dormancy in which their metabolic processes almost entirely cease, allowing them to withstand periods of cosmic radiation and near absolute zero temperatures. When enclosed within rocks, these organisms gain additional protection. The outer layers of rock absorb most of the radiation, and the interior of the rock provides insulation against both heat and cold. Lithopanspermia is supported not just by theoretical models, but by concrete evidence from meteorite studies. Over the decades, scientists have discovered meteorites originating from the Moon and Mars on Earth, confirming that rocks can indeed be naturally ejected from planetary surfaces and traverse space. One famous example is the Allen Hills 84001 meteorite from Mars, which contains microscopic structures that some scientists argue could be fossilized microbial life. While this interpretation remains debated, the mere presence of Martian rock on Earth proves the feasibility of rocks traveling between planets. These findings make the concept of lithopanspermia more than just a theoretical construct. It is a real cosmic phenomenon that could have played a role in distributing life. An intriguing aspect of lithopanspermia is that it is not restricted to planets in the same solar system. In principle, interstellar lithopanspermia could occur, though the timescales and probabilities decrease drastically. Rocks carrying microbial life could, over millions or even billions of years, be ejected from one star system, travel through interstellar space, and eventually be captured by another star's planetary system. While the likelihood of survival decreases with longer travel times and exposure to cosmic radiation, research suggests that microorganisms deeply embedded in large enough rock fragments could survive even these extreme journeys. In essence, rocks act as natural interstellar lifeboats, capable of protecting the delicate cargo of life over mind-boggling distances. The concept of lithopanspermia also reshapes our understanding of the early solar system. The late heavy bombardment period, roughly 4 billion years ago, saw the inner planets, including Earth, Mars, and Venus, bombarded with an extraordinary number of asteroids and comets. These violent collisions would have created enormous amounts of planetary ejecta, drastically increasing the chances that rocks containing microorganisms could be flung from one world to another. Mars, with its lower gravity compared to Earth, is particularly suited for this process. A single impact on the Martian surface could easily eject rocks into space, some of which may have eventually made their way to Earth, potentially seeding life here. This has led some scientists to speculate that if life arose first on Mars, Panspermia could have delivered it to Earth during this period of cosmic chaos. Beyond the mechanics of survival and transport, Panspermia raises profound philosophical questions about the interconnectedness of life in the cosmos. If life on Earth arrived from another planet, it implies that life is not a strictly local phenomenon, but part of a broader cosmic ecosystem. Every organism on Earth could be a descendant of life that originated on a different world entirely, carrying genetic blueprints that were shaped elsewhere before being refined here. It also means that Earth might not be unique in hosting life. Other planets, both in our solar system and beyond, could harbor life forms that share a common ancestry with life here. Another compelling implication of Panspermia is the potential for genetic continuity across planets. Microorganisms transported between planets would likely bring with them pre-existing genetic material. If they successfully colonized another world, evolution would take over, but the initial seed DNA could influence the trajectory of life on that planet. This raises the fascinating possibility that life throughout the cosmos might share fundamental biochemical traits, such as the same basic nucleotides in DNA and RNA, because they descended from the same ancestral microorganisms scattered via Panspermia. It creates a vision of life as a shared heritage, spanning planets and possibly star systems, all linked by the journeys of microscopic pioneers riding on cosmic rocks. Critically, Panspermia is not purely a theoretical exercise. It is supported by physics, biology, and observational evidence. Computer simulations have modeled the trajectories of ejected planetary debris and demonstrated that collisions can indeed propel rocks at escape velocity, send them into orbits that intersect other planetary bodies, and deliver them safely over millions of years. Laboratory experiments have demonstrated microbial resilience under vacuum conditions, high-energy radiation, and repeated thermal cycling, further supporting the notion that life could survive the journey. The combined evidence suggests that Panspermia is not only possible, but could plausibly explain how life spread across planets in our solar system, or even seeded multiple worlds. The beauty of Panspermia lies in its simplicity. Life does not need to emerge independently on every planet. It simply needs a mechanism for transportation. Rocks blasted off by natural impacts, carrying hardy microorganisms sheltered in their interiors, provide exactly such a mechanism. The universe, in this sense, acts as a vast laboratory, experimenting with life across worlds and time, distributing it wherever conditions are suitable. If Panspermia is a reality, it reshapes our understanding of life, not as an isolated earthbound phenomenon, but as a cosmic process that can transcend planetary boundaries. Every microbe, every genetic strand, could carry the imprint of a journey that began millions of years ago on a planet far from Earth. The plausibility of panspermia relies heavily on the remarkable resilience of certain microorganisms known as extremophiles, which thrive in conditions once thought to be completely inhospitable to life. On Earth, extremophiles inhabit environments ranging from boiling acidic springs and deep ocean hydrothermal vents to polar ice caps and the near vacuum of high-altitude deserts. Their ability to endure extreme temperatures, high pressures, desiccation, and intense radiation demonstrates that life is far more adaptable than traditionally imagined, making the notion of life surviving space travel not just possible, but scientifically credible. Radiation, for example, is one of the greatest challenges life would face during interplanetary or interstellar journeys. In space, cosmic rays and solar radiation can easily damage DNA and other essential biological molecules. Yet certain extremophiles, such as Deinococcus radiodurans, can survive radiation doses thousands of times higher than what would be lethal to humans. This bacterium can repair its DNA even after it has been shattered into dozens of fragments, effectively making it radiation-proof under conditions that would destroy ordinary life. Such capabilities are crucial for the panspermia hypothesis because they provide a realistic model for how microorganisms might endure prolonged exposure to space radiation while encased in rocks or comets. Extremophiles also exhibit extraordinary tolerance to vacuum and desiccation. For example, tardigrades, microscopic water bears, can survive the vacuum of outer space, completely dehydrating themselves into a ton state in which their metabolism nearly stops. Once rehydrated, they can resume normal biological activity, making them living proof that organisms can endure extreme environmental stress for extended periods. Similarly, spores of certain bacteria and fungi can remain dormant for decades, centuries, or potentially millennia, protected by their tough outer layers, awaiting conditions suitable for growth. Such durability makes it plausible that microorganisms embedded within meteors or comets could survive the millions of years necessary for interplanetary travel. Temperature extremes pose another formidable obstacle. Space can be frigid, with temperatures dropping to near absolute zero. Yet, extremophiles have demonstrated resilience in these conditions as well. Some psychrophilic organisms thrive at temperatures well below freezing, producing antifreeze proteins and stabilizing their cellular structures to prevent damage from ice crystal formation. In a space environment, microorganisms frozen within cometary ice could remain in stasis, metabolically dormant, but fully capable of reactivating when conditions allow, such as during atmospheric entry onto a warm planet. Conversely, the heat generated during planetary impacts or atmospheric entry might seem lethal, yet the interiors of rocks can remain surprisingly cool, providing a natural protective shield that extremophiles could exploit. These extraordinary adaptations underscore a profound truth. Life is far more resilient than we once imagined, capable of surviving conditions that would have seemed impossible to early scientists. Extremophiles are the living models that make panspermia scientifically plausible. They demonstrate that microorganisms could survive the vacuum of space, extreme radiation, intense cold, and the mechanical stresses of impact events, all while lying dormant until they reach a hospitable environment. Without extremophiles, panspermia would remain a speculative fantasy, but their existence bridges the gap between theoretical possibility and biological reality. Furthermore, extremophiles hint at the versatility and universality of life's chemistry. Many extremophiles utilize robust biochemical pathways, repair mechanisms, and structural adaptations that could theoretically function in extraterrestrial environments. Their existence suggests that life does not require perfect, Earth-like conditions to survive, but can persist under a wide array of stresses. This adaptability not only supports the concept of lithopanspermia within our own solar system, but also expands the realm of possibility to interstellar panspermia, where microorganisms could traverse light years and still arrive capable of initiating life on distant worlds. Microbial survivors, particularly extremophiles, provide the critical foundation for the panspermia hypothesis. Their ability to withstand radiation, vacuum, temperature extremes, and desiccation demonstrates that life can endure the harsh conditions of space travel. They are the biological proof that the cosmos could indeed be a vast conveyor belt for life, transporting it across planets, star systems, and potentially even galaxies. With extremophiles as living evidence, the notion that life on Earth may have originated elsewhere becomes not just a fascinating speculation, but a scientifically plausible scenario, bridging the gap between cosmic mechanics and biological resilience. Among the many tantalizing possibilities in the panspermia hypothesis, Mars stands out as one of the most compelling candidates for the origin of life that may have later spread to Earth. For decades, scientists have been captivated by the similarities between early Earth and ancient Mars. Both planets formed in the same protoplanetary disk, experienced intense bombardment from asteroids and comets, and likely hosted liquid water on their surfaces during their formative years. Evidence from Martian meteorites, satellite imagery, and rover missions suggests that ancient Mars had rivers, lakes, and possibly even oceans, creating environments capable of supporting microbial life. The notion that Earth life may have been seeded from Mars is known as the Mars-to-Earth lithopanspermia hypothesis, and it has grown increasingly plausible in light of modern discoveries in planetary science, astrobiology, and microbiology. The Martian hypothesis begins with the premise that early Mars, perhaps 4 billion years ago, was warmer and wetter than it is today. Geological studies indicate the presence of extensive river valleys, lake beds, and mineral deposits formed in the presence of water. These environments could have provided the stable conditions necessary for primitive life to emerge. Some scientists argue that Mars may have even offered better conditions for the emergence of life than early Earth. While Earth was subject to intense tectonic activity, volcanic eruptions, and frequent impacts that could have sterilized nascent life, Mars's smaller size and less active geology might have allowed life to persist in relatively isolated niches, protected from catastrophic events. Once life had emerged on Mars, the question becomes, how could it have reached Earth? This is where lithopanspermia plays a crucial role. Mars's lower gravity compared to Earth means that impacts by large asteroids or comets could more easily eject rocks into space. These rocks could contain dormant microorganisms, shielded deep within their interiors, and travel the tens of millions of kilometers to Earth over timescales of thousands to millions of years. Remarkably, studies of Martian meteorites found on Earth, such as the famous ALH 84001, show that rocks can indeed survive the journey intact. These meteorites are physical proof that material from Mars can naturally reach Earth, lending tangible credibility to the idea that life might have traveled along with them. Adding to the intrigue, certain chemical signatures in these meteorites hint at biological activity, though this remains highly debated. ALH 84001, for instance, contains carbonate globules, magnetite crystals, and polycyclic aromatic hydrocarbons that some scientists suggest could be remnants of ancient Martian microorganisms. While skeptics argue that non-biological processes can produce similar structures, the presence of these compounds continues to fuel speculation that Mars could have harbored life long before Earth became hospitable. If these microbial seeds were indeed present in Martian rocks, it becomes plausible that they were transported to Earth via meteoritic impacts, potentially kick-starting life here billions of years ago. Moreover, the Mars-to-Earth panspermia scenario addresses one of the central puzzles of life on our planet: its surprisingly rapid emergence. Geological and isotopic evidence suggests that life appeared on Earth almost as soon as conditions stabilized enough to support it, around 3.8 to 4 billion years ago. Given the volatile conditions on early Earth, frequent asteroid impacts, unstable climates, and extreme volcanism, the emergence of life so quickly seems improbable if Earth were the sole cradle of life. However, if life had already originated on Mars and arrived here via lithopanspermia, it could explain how life appeared almost immediately once Earth became hospitable. In this scenario, Earth is not the birthplace of life, but a fertile incubator where life from elsewhere could take hold and evolve. Recent studies in astrobiology also highlight the resilience of microbial life to the journey from Mars to Earth. Experiments simulating ejection from a planetary surface, long-term exposure to vacuum and radiation, and atmospheric entry indicate that microbes embedded deep within rocks could survive these extreme conditions. Extremophiles capable of withstanding desiccation, radiation, and temperature extremes, like those discussed earlier, could remain dormant for the thousands to millions of years required to reach Earth. Upon arrival, these microorganisms could awaken and begin to proliferate in Earth's watery environments, initiating the long evolutionary process that eventually led to the diversity of life we see today. Mars's status as a potential life source also gains support from its chemical composition and planetary history. The planet contains significant quantities of essential elements for life, including carbon, nitrogen, phosphorus, and sulfur. Its ancient climate, although harsh by Earth standards, may have been conducive to prebiotic chemistry and the formation of organic compounds. Observations by orbiters and rovers have revealed the presence of clays, sulfates, and other minerals that form in the presence of water, suggesting that Mars once had stable, long-lasting, aqueous environments, prime conditions for life to originate. In this context, Mars may not just be a candidate for life elsewhere in our solar system, but a direct contributor to life on our own planet. The philosophical and scientific implications of a Martian origin for life are profound. If Earth life descended from Martian microorganisms, then our biosphere is directly linked to another planet, redefining what it means to be native to Earth. Life would no longer be an isolated phenomenon, but part of an interplanetary continuum, a narrative in which planets exchange the fundamental building blocks of biology. It also expands our search for life in the universe. If life can survive on Mars and spread to Earth, it may similarly traverse between other planets and moons in our solar system, or even between star systems across the galaxy. Europa, Enceladus, and Titan could harbor life, either indigenous or delivered via similar cosmic processes, emphasizing that life is potentially widespread and interconnected in ways we are only beginning to understand. The Mars-to-Earth Panspermia hypothesis also inspires speculation about the future of humanity. If life can naturally travel between planets, it may be possible for us, as a technologically advanced species, to intentionally carry life to other planets' worlds, effectively participating in the same cosmic process that may have brought life here. Such a perspective reinforces the idea that life is not confined to a single planet, but can expand and evolve wherever conditions permit. The potential connections between Martian and Earth life also remind us of the shared history we may have with other planets, suggesting that the story of life is not isolated but cosmic, spanning worlds, time, and perhaps even star systems. While definitive proof that life originated on Mars and migrated to Earth remains elusive, the convergence of planetary science, meteorite studies, and microbial biology makes it a compelling scenario. The Martian hypothesis elegantly explains the rapid appearance of life on Earth, aligns with physical evidence of material exchange between planets, and fits within the broader framework of panspermia. It also emphasizes a universe in which life is not a singular occurrence, but a phenomenon capable of moving, surviving, and evolving across planets. If correct, this idea transforms our understanding of life's origin from a purely terrestrial process into a cosmic narrative, suggesting that every organism on Earth may carry a genetic legacy that began on Mars billions of years ago. While the Mars-to-Earth hypothesis presents a compelling local example of panspermia, the concept can be extended even further into the vastness of interstellar space. The interstellar angle of panspermia proposes that life on Earth might not even be native to our solar system, but could have arrived from a distant star system, traveling across the galaxy over millions or even billions of years. This idea challenges our understanding of life's origin in ways that are both profound and humbling, suggesting that Earth might be just one node in a sprawling, galaxy-wide network of life. The plausibility of interstellar panspermia rests on both astrophysical mechanisms and the extraordinary resilience of life. Stars form in clusters, often within dense molecular clouds composed of gas and dust. Planetary systems form from the same rotating disks of material, and the early solar system itself likely experienced encounters with nearby stars. In such environments, gravitational interactions could hurl planetary debris, some potentially harboring microorganisms, into interstellar space. These ejecta, if large enough, could shield embedded microbes from lethal cosmic radiation while traversing light years to reach another planetary system. Even though interstellar travel presents far greater challenges than travel within a single solar system, the sheer timescales involved make it theoretically possible for life to endure such voyages. Evidence supporting the feasibility of interstellar travel for microorganisms comes from studies of cosmic dust, comets, and meteorites. Organic molecules such as amino acids, nucleobases, and sugars have been detected in meteorites and interstellar clouds, indicating that the chemical precursors for life are widespread throughout the galaxy. These findings suggest that not only the building blocks of life, but potentially life itself, could exist beyond our solar system. If hardy microorganisms can survive long-term exposure to space within protective fragments of rock or ice, the possibility arises that Earth life could be descended from distant extraterrestrial sources, predating even the formation of our own Sun. One of the most intriguing pieces of the interstellar panspermia puzzle is the discovery of exoplanets in habitable zones around distant stars. With thousands of exoplanets confirmed in the past few decades, many of which orbit within their star's Goldilocks zone, where liquid water could exist, the potential for life beyond our solar system has shifted from speculative to plausible. If life could evolve on one of these planets and subsequently be ejected into interstellar space via impacts, it could traverse the void and potentially arrive at a young, hospitable world such as early Earth. The notion of life as a galaxy-spanning phenomenon transforms our perspective, suggesting that planets within the Milky Way may not be isolated incubators, but part of a dynamic exchange of biological material. Interstellar panspermia also provides a potential explanation for some puzzling features of life on Earth. For example, the sudden appearance of complex molecules in the early geological record, or the apparent universality of DNA and RNA across all known organisms, could be consistent with a single, ancient source of life that predated our solar system. If life arrived from elsewhere, it might have carried with it genetic templates or preformed biochemical pathways that gave life on Earth a head start, enabling it to flourish rapidly once the planet became suitable. In this context, the shared molecular machinery of all living organisms could be viewed as evidence of a common ancestral seed that originated far beyond our solar system. Astrophysical modeling suggests that even though interstellar distances are immense, material can travel between star systems through natural processes. For instance, Oort cloud objects, which inhabit the outer edges of our solar system, could be ejected by gravitational interactions with passing stars, carrying with them the potential for microbial life. Similarly, planetary impacts could accelerate ejecta to escape velocity, sending them into interstellar trajectories. While the odds of a specific rock reaching another habitable planet are low, the vast number of stars, planets, and potential ejection events across the Milky Way increases the cumulative probability that life could have spread from one system to another over cosmic timescales. Another fascinating aspect of interstellar panspermia is its implication for the distribution of life throughout the galaxy. If life on Earth originated from beyond our solar system, it is plausible that other planets may also harbour life with a common ancestry. The galaxy itself could be envisioned as a network of interconnected life-bearing worlds, where planets exchange microorganisms and organic material across vast distances. This perspective transforms life from a purely planetary phenomenon into a galaxy-wide process, suggesting that living systems may be fundamentally interconnected across stellar systems. It also raises profound philosophical questions. Are we truly from Earth? Or are we part of a lineage that traces back to distant stars, carried here by cosmic events over eons? Interstellar panspermia also intersects with the search for extraterrestrial life. If life can naturally travel between star systems, it increases the probability that planets orbiting nearby stars could already host life or have been seeded in a similar way. Missions aimed at detecting biosignatures on exoplanets, analysing the atmospheres of distant worlds, or studying cometry and asteroidal material could provide indirect evidence supporting this theory. Additionally, the discovery of complex organic molecules in interstellar clouds suggests that the ingredients for life, and potentially life itself, are far more widespread than previously thought. This lends weight to the idea that Earth is not unique, but part of a much larger, living cosmos. While interstellar panspermia remains speculative, it builds on the same principles that make lithopanspermia and Martian panspermia plausible. Resilient microorganisms, protective cosmic carriers, and the dynamic, interconnected nature of planetary systems. Extremophiles could survive the vacuum of space, shielded inside rocks or icy comets, enduring cosmic radiation and extreme temperatures for millions of years. Gravitational interactions and stellar dynamics could propel these carriers across interstellar distances. Organic molecules and prebiotic compounds found in meteorites and interstellar clouds demonstrate that the raw materials of life are abundant and widespread. Taken together, these elements create a scientifically credible framework for the idea that life on Earth might have originated far beyond our solar system, perhaps billions of years before our Sun was even born. The interstellar angle of panspermia ultimately reframes our understanding of life in the universe. It suggests that life is not a rare, localized accident, but a potentially universal process, capable of traversing the void between stars, enduring unimaginable conditions, and taking root wherever circumstances allow. If true, it implies that our planet is just one node in a vast galactic network of life, connected to distant worlds by ancient and invisible threads. Humanity's genetic legacy could, in fact, trace back to planets and star systems we have never seen, expanding the story of life beyond Earth and into the cosmos itself. One of the most compelling lines of evidence supporting panspermia comes from the study of meteorites that have fallen to Earth from space. These space rocks serve as natural time capsules, carrying within them chemical signatures and, in some cases, structures that hint at the possibility of life beyond our planet. Meteorites are fragments of asteroids, comets, and even other planets, and they can preserve both organic molecules and minerals formed in the early solar system, offering a rare glimpse into the materials and processes that existed long before life appeared on Earth. Over decades of research, scientists have uncovered a wealth of information within these extraterrestrial visitors, providing tantalizing evidence that the ingredients of life, and possibly life itself, exist throughout the cosmos. One of the most significant discoveries in meteorites is the presence of organic molecules, the carbon-based compounds that form the building blocks of life. Among these are amino acids, which are essential for constructing proteins, as well as nucleobases, which form the basis of DNA and RNA. Perhaps the most famous example comes from the Murchison meteorite, which fell in Australia in 1969. Researchers found over 70 different amino acids in this meteorite, many of which are not commonly found on Earth. The diversity and abundance of these molecules indicate that the chemical precursors to life can form naturally in space, independent of Earthbound processes. This challenges the traditional view that life's building blocks had to originate on Earth itself, supporting the idea that material capable of forming life could arrive from extraterrestrial sources. In addition to amino acids and nucleobases, meteorites have also been found to contain sugars, fatty acids, and other complex organic compounds. These discoveries suggest that prebiotic chemistry, the chemical processes that lead to the formation of life, may be universal. Laboratory simulations have shown that such molecules can form under conditions found in space, including within interstellar clouds, comets, and icy planetary bodies. Meteorites act as delivery vehicles, bringing these essential compounds to Earth in a form that could potentially kickstart the processes of life, much as a seed might sprout when planted in fertile soil. Beyond the chemical evidence, some meteorites appear to contain physical structures that resemble microbial fossils. The most debated example is the Martian meteorite, ALH84001, which contains tiny, filamentous formations that some scientists have argued could be fossilized bacteria. While this interpretation remains controversial, many researchers argue that these structures could be produced by non-biological processes. The discovery has nonetheless sparked intense interest and investigation into the possibility that life, or evidence of life, exists beyond Earth. These potential microbial structures, if confirmed as biological in origin, would provide direct support for the idea that life can travel between planets, surviving the harsh conditions of space embedded within rocks. Meteorites also provide insights into the types of environments that could harbor life elsewhere in the solar system. Many meteorites contain minerals that formed in the presence of water, such as clays and carbonates, indicating that water-rich environments exist, or existed, beyond Earth. Since liquid water is a crucial component for life as we know it, these findings strengthen the plausibility of life having arisen or survived on other planetary bodies before being transported to Earth. Moreover, the detection of isotopic ratios in these meteorites, such as variations in carbon and nitrogen isotopes, sometimes hints at biological processing, further fueling speculation that life, or at least the chemical precursors of life, may be widespread in space. The study of meteorites also highlights the robustness of life in space. Rocks ejected from planetary surfaces can travel millions of kilometers, enduring cosmic radiation, vacuum, and extreme temperatures, yet still deliver intact organic compounds to other worlds. The very fact that amino acids, sugars, and complex organics have survived these journeys suggests that microbial life could similarly endure interplanetary or even interstellar transport. This aligns closely with the findings from extremophiles on Earth, which demonstrate that life can survive the most extreme conditions, providing a biological mechanism for how panspermia could work in practice. Meteorites not only offer chemical and potential biological evidence, but also provide a historical record of the solar system's early conditions. Many meteorites date back over 4.5 billion years, predating the formation of Earth's stable crust and oceans. This means that the organic compounds and possible microbial structures they carry could have existed long before life emerged on Earth, implying that our planet may have received these life-seeding materials very early in its history. This timing could explain why life appeared so quickly on Earth once conditions stabilized. Seeds may have already been delivered, lying dormant until the right environment allowed them to flourish. In recent years, meteorites have also been studied in the context of interstellar material. Some rare specimens, identified by their unusual isotopic signatures and chemical composition, may have originated from beyond our solar system. These findings suggest that not only can life-bearing or life-precursor materials travel between planets, but they might also traverse star systems, providing further plausibility for interstellar panspermia. If confirmed, this would radically expand our understanding of life's potential distribution across the galaxy, hinting that Earth may be just one recipient of a vast, cosmic network of life-seeding material. Ultimately, meteorites serve as tangible evidence that the universe contains the ingredients necessary for life, and that these ingredients can survive the harsh conditions of space travel. The presence of amino acids, sugars, nucleobases, water-altered minerals, and even potential microbial fossils in meteorites bridges the gap between theory and observation, giving weight to the panspermia hypothesis. They show that life, or at least the components that make life possible, is not confined to Earth, but is a cosmic phenomenon scattered across planets, comets, asteroids, and perhaps even interstellar clouds, ready to seed new worlds whenever conditions allow. Comets have long captured humanity's imagination, often portrayed as harbingers of change streaking across the night sky. Beyond their visual spectacle, comets may play a far more profound role in the history of life, acting as cosmic delivery vessels capable of transporting the essential ingredients of life, and potentially life itself, across the solar system. Composed primarily of water ice, frozen gases, dust, and organic compounds, comets are remnants of the early solar system, preserving the raw materials from which planets and life evolved. Their unique composition and long-distance mobility make them ideal candidates for distributing the seeds of life, either through natural impacts with planets or by gradually depositing organic-rich material as they travel through space. The abundance of water ice in comets is particularly significant. Water is essential for all known life because it acts as a solvent, facilitating the chemical reactions necessary for metabolism. Comets are essentially giant frozen reservoirs of water, often containing more than 50% water ice by mass. As a comet approaches the Sun, the ice sublimates, creating a temporary atmosphere, or coma, and releasing dust and organic compounds into space. This process can scatter complex molecules over a wide area, potentially delivering them to nearby planets or moons. In this way, comets could have contributed not just to the chemical inventory of Earth, but also to the very genesis of life by depositing water and prebiotic molecules directly onto its surface. Comets are also rich in organic compounds, including amino acids, hydrocarbons, and sugars, which are fundamental to life. These molecules have been detected both in cometary dust and in the gases emitted by comets during solar heating. The European Space Agency's Rosetta mission to Comet 67P/Churyumov-Gerasimenko, for example, revealed the presence of complex organic molecules such as glycine, the simplest amino acid, and phosphorus, a key element in DNA and RNA. Such discoveries suggest that comets are not mere rocks, but repositories of complex chemistry, capable of delivering molecular building blocks necessary for life. When these compounds land on a planetary surface, they could provide the raw materials for prebiotic chemistry to take place, setting the stage for the emergence of life. Beyond chemical delivery, comets could also protect life during interplanetary travel. Microorganisms, or prebiotic molecules encased in icy matrices, could be shielded from ultraviolet radiation, cosmic rays, and the vacuum of space. The ice acts as a natural insulator, preserving these compounds for potentially millions of years as the comet traverses the solar system or beyond. Some comets even travel on trajectories that cross multiple planetary orbits, increasing the likelihood of colliding with a habitable world. In such cases, the comet could deposit its cargo directly onto the planet's surface, effectively planting the seeds of life. The role of comets extends beyond their function as carriers of organic compounds. They may have also contributed to Earth's water. Some theories suggest that a significant portion of Earth's oceans could have been delivered by cometary impacts early in the planet's history. If water and organic molecules arrived together, comets could have provided both the solvent and the chemical building blocks necessary for life, creating a favorable environment for the first organisms to emerge. This dual delivery system enhances the plausibility of panspermia, suggesting that comets could simultaneously supply the materials and conditions essential for life to thrive. The dynamics of cometary orbits further support their potential as life delivery vehicles. Comets often originate from the distant Oort cloud or the Kuiper belt, reservoirs of icy bodies at the edge of the solar system. Gravitational perturbations from passing stars or giant planets can send comets spiraling inward, crossing the inner solar system and occasionally colliding with planets. These long-range journeys offer a mechanism for distributing life or organic material across vast distances, linking distant regions of space to the environments where life can emerge. Unlike asteroids or meteoroids, comets can carry large amounts of ice and organics, giving them a unique advantage as both protectors and transporters of prebiotic material. In addition, the impact of a comet on a planetary surface could have dramatic biological consequences. The energy released during such impacts can be immense, capable of melting ice, vaporizing rock, and creating transient liquid water environments. While catastrophic in some ways, these impacts may have also provided niches for life to emerge, combining heat, water, and organic molecules in ways that promote prebiotic chemistry. Cometary impacts could therefore serve a dual function, delivering life-sparking ingredients and generating localized conditions conducive to the emergence of early life. Comets also tie naturally into interstellar panspermia scenarios. Some comets, particularly those from the distant Oort cloud, may originate from outside our solar system. These interstellar comets could, in theory, carry complex organic molecules or even dormant microorganisms from other star systems, acting as vehicles for the distribution of life across the galaxy. The discovery of 1I/Oumuamua, an interstellar object passing through our solar system in 2017, demonstrates that objects from other star systems can indeed traverse interstellar space. If such objects carry the chemical or biological precursors of life, it is conceivable that life on Earth, or elsewhere in the galaxy, could have an origin that predates the formation of our own solar system. The role of comets in the panspermia hypothesis highlights the interconnectedness of celestial bodies in fostering life. Earth is not isolated in its potential to develop life. It receives materials, energy, and even potential microbial life from a network of cosmic travelers. Comets, as rich repositories of ice and organics, act as crucial links in this network, carrying life's raw ingredients across space and time. By delivering water, complex organic molecules, and potentially even dormant microorganisms, comets help bridge the gap between the chemistry of space and the biology of planets, making the emergence of life on Earth, or its seeding from elsewhere, a plausible, if extraordinary, event. One of the most formidable hurdles for panspermia is the question of survival. Even if life could hitch a ride on meteoroids, comets, or planetary ejecta, could it endure the extreme conditions of space travel and then survive the fiery entry into a planetary atmosphere? The survival challenge encompasses two primary threats: the constant bombardment of cosmic radiation during interstellar or interplanetary travel, and the intense heat and mechanical stress encountered upon atmospheric entry. Both factors pose significant threats to organic molecules and microorganisms, yet studies of extremophiles and protective mechanisms suggest that life may be far more resilient than previously thought. Cosmic radiation, primarily composed of high-energy protons and atomic nuclei, is one of the most severe challenges for life in space. These energetic particles can break chemical bonds, destroy DNA and RNA, and generate reactive oxygen species that damage cellular components. Over millions of years of exposure, even dormant microorganisms risk being rendered non-viable. However, life on Earth has already provided remarkable examples of resilience. Certain extremophiles, such as Deinococcus radiodurans, can survive doses of radiation thousands of times higher than lethal levels for humans. These microbes have exceptional DNA repair mechanisms, capable of reconstructing their genome even after it has been shattered into fragments. By analogy, microorganisms encased within rocks or ice could endure the background radiation of space, particularly if shielded by several centimeters of rock or cometary material, which absorb and deflect much of the radiation. Shielding is critical. Studies suggest that a rock several centimeters thick can dramatically reduce radiation exposure, protecting embedded microorganisms over timescales sufficient for interplanetary travel. Even during interstellar journeys lasting millions of years, these protective layers could preserve life in a state of dormancy, allowing it to remain viable until reaching a hospitable environment. Water ice within comets provides an additional layer of insulation, absorbing radiation and shielding organic molecules or dormant microbes from the full brunt of cosmic rays. This combination of natural shielding and biological resilience greatly enhances the plausibility that life could survive the otherwise inhospitable conditions of space. Mechanical stress and extreme temperatures during ejection and atmospheric entry represent another significant barrier. When a meteorite is blasted off a planetary surface by a massive impact, the forces involved are immense, generating shock waves that can exceed thousands of atmospheres of pressure. Microorganisms embedded within the interior of these rocks, however, may be largely protected from these shocks. Experiments simulating hypervelocity impacts on bacterial spores show that microbes can survive these extreme pressures if they are located deep within the ejector. Furthermore, the interior of a rock heats much less than its surface during both ejection and re-entry, providing a natural thermal shield that could protect life from temperatures that would otherwise sterilize exposed organisms. Atmospheric entry presents a particularly dramatic challenge. As a meteoroid or comet fragment plummets toward Earth, friction with the atmosphere generates intense heat, often exceeding thousands of degrees Celsius on the surface. While the outer layers of the rock can be vaporized or melted, the interior can remain relatively cool, particularly for larger rocks with diameters of tens of centimeters or more. Computational models and laboratory experiments indicate that microbial life embedded in the interior of such meteoroids could remain viable, shielded from extreme heat and mechanical stress. Even for icy bodies like comets, sublimation of surface ice during entry may protect interior pockets of frozen water and organic compounds, preserving potential life. The combination of radiation shielding, dormancy, and protection within rocks or ice means that survival through interplanetary travel and atmospheric entry is plausible. Extremophiles provide a natural template, demonstrating that life can endure conditions once thought lethal, from vacuum and desiccation to radiation and temperature extremes. In laboratory simulations, bacterial spores have survived multiple cycles of freezing, vacuum exposure, and high radiation doses, all conditions analogous to what life would encounter during panspermia. These findings underscore the remarkable adaptability of life and suggest that cosmic delivery of microorganisms is not just a theoretical possibility, but a process supported by both physical and biological evidence. Additionally, life may not need to survive intact for panspermia to succeed. Even the delivery of prebiotic organic molecules, such as amino acids, nucleobases, and sugars, could provide the raw materials necessary for life to emerge anew on a planet. In this sense, panspermia could function in a spectrum, from the transfer of fully viable microorganisms to the transfer of the chemical building blocks that seed life, both of which would enable the continuation of life across space and time. This flexibility further increases the plausibility of the hypothesis, suggesting that life, or the potential for life, can endure and spread in ways previously unimagined. The survival challenge also emphasizes the role of chance and scale in panspermia. While the probability of any single microbe surviving a long journey and successfully landing in a hospitable environment may be low, the vast number of meteoroids, comets, and ejecta traveling through the solar system and potentially beyond means that statistically the process is feasible. Billions of potential carriers over millions of years provide countless opportunities for successful seeding events, making the interplanetary and interstellar distribution of life a viable mechanism. While the survival challenge is formidable, it is not insurmountable. Life, particularly in the form of extremophiles, possesses remarkable strategies for enduring radiation, vacuum, temperature extremes, and mechanical stress. Protective carriers such as rocks and icy comets amplify these capabilities, offering natural shielding for life during both the journey through space and the fiery passage into a planetary atmosphere. Whether as dormant microorganisms or as prebiotic molecules, life has the potential to survive the extreme conditions of space travel and emerge ready to thrive in a suitable environment. By demonstrating that life can overcome these challenges, the survival aspect of panspermia transforms the concept from science fiction into a scientifically credible scenario, highlighting the resilience and universality of life. Beyond the natural mechanisms of panspermia lies an even more provocative and speculative idea: directed panspermia. Whereas natural panspermia relies on cosmic debris, cometary ice, and planetary ejecta to transport life passively through space, directed panspermia posits that intelligent civilizations could deliberately seed planets with life, effectively spreading biology as an intentional act. This concept was first formally proposed in 1973 by Nobel laureate Francis Crick, one of the discoverers of the DNA double helix, and biologist Leslie Orgel. They suggested that life on Earth might have been deliberately planted by an advanced extraterrestrial civilization, either as an experiment, as a method of self-preservation, or even as a cosmic legacy intended to ensure the continuation of life throughout the universe. The appeal of directed panspermia lies in its ability to address some of the persistent mysteries surrounding life's origin. One of the greatest puzzles is the rapid emergence of life on Earth once conditions became suitable, alongside the complexity of even the earliest known life forms. Natural chemical evolution, while theoretically possible, struggles to explain how life could arise so quickly in a relatively unstable environment. Directed panspermia introduces a scenario in which life was not constrained to originate from scratch on Earth, but rather arrived fully equipped to begin replicating and evolving. In this model, Earth may have been seeded with microbes or prebiotic molecules that were already biologically active or primed for rapid development. The mechanisms by which a civilization could carry out directed panspermia are as fascinating as they are speculative. Advanced beings might have utilized spacecraft or sterilized delivery systems to transport microbial life across space, embedding it within protective shells to survive cosmic radiation and the vacuum of interstellar travel. These spacecraft could be deliberately aimed at planets within habitable zones, timed to arrive when environmental conditions were most favorable for life to take hold. Alternatively, a civilization could spread life indirectly, sending out numerous life-bearing probes or even manipulating asteroid trajectories to distribute organisms passively, ensuring a higher probability that at least some of these life-seeding events succeed. The hypothesis also raises questions about the motivations of such civilizations. One possibility is that they viewed life as valuable enough to propagate intentionally, seeking to expand the diversity and presence of life across the cosmos. Another is that they aim to ensure their own legacy, a form of cosmic immortality achieved by creating descendants across multiple worlds. There is also the notion that seeding life could be part of a grand experiment in planetary evolution, allowing intelligent beings to observe how life develops under different conditions. Regardless of the motivation, directed panspermia suggests that life on Earth might be part of a broader, intentional network, linking our planet to a galactic biosphere created by other, perhaps long-extinct, civilizations. Directed panspermia intersects intriguingly with the universality of DNA and RNA observed in all known life. If a single origin of life were seeded intentionally, it could account for the shared biochemical architecture that underlies every organism on Earth. The universality of genetic coding, the common use of the same amino acids, and the remarkable similarity of fundamental metabolic processes might reflect not just evolutionary constraints, but a deliberate design by an intelligent seeder. In this sense, the shared genetic language of life could be interpreted as a signature left behind by the civilization that initiated it, a form of cosmic fingerprint encoded in the very molecules that sustain life. Some proponents of directed panspermia even suggest that the advanced civilization responsible might have seeded life elsewhere as well, creating a galaxy-wide network of biologically connected planets. This scenario implies that Earth is not unique, but one node in a vast system of life-bearing worlds intentionally nurtured or influenced by a higher intelligence. Such a perspective radically expands the scope of panspermia, framing the evolution of life on Earth not as an isolated accident, but as part of a deliberate, universe-spanning strategy. It also invites the possibility that life elsewhere in the cosmos could share fundamental similarities with life on Earth, a consequence of deliberate distribution rather than convergent evolution. While directed panspermia is highly speculative and lacks direct evidence, it remains scientifically provocative because it can be tested indirectly. For instance, if we detect life elsewhere in the solar system or on exoplanets and find that its biochemical structures are remarkably similar to terrestrial life, it might suggest a shared origin beyond Earth. Conversely, if extraterrestrial life is entirely different, it could support the idea that life arises independently in multiple places. Future exploration of Mars, Europa, Enceladus, Titan, and exoplanets may therefore provide crucial insights into whether life's spread is natural, directed, or a combination of both. Critics of directed panspermia argue that it raises more questions than it answers, such as the origin and motivations of the seeding civilization and how it survived the immense timescales involved. Yet, even as a thought experiment, directed panspermia highlights the extraordinary possibility that life on Earth may not have been a random accident, but a deliberate act by beings capable of engineering life across planets. It challenges humanity's perception of itself as the sole product of earth-bound evolution and reframes life as part of a potentially intentional cosmic legacy stretching across space and time. One of the most intriguing pieces of evidence in favor of a single origin of life, whether terrestrial or extraterrestrial, lies within the very molecules that govern life itself: DNA and RNA. Across the diversity of life on Earth, from the simplest bacteria to the most complex mammals, there is a striking universality in the structure and function of these nucleic acids. All organisms use the same 4 nucleotides in DNA: adenine, thymine, guanine, and cytosine. And nearly all life employs the same 20 amino acids to build proteins. This biochemical uniformity strongly suggests that all known life shares a common ancestry, stemming from a single progenitor organism, often referred to as the last universal common ancestor, LUCA. But what if LUCA itself was not Earthborn? Could the shared genetic blueprints be evidence that life's origin lies beyond our planet, perhaps delivered here via panspermia? The consistency in genetic coding across life is remarkable. DNA sequences are read in codons, 3 nucleotide units, which specify the same amino acids in virtually all organisms. RNA, as the intermediary that translates DNA into proteins, also functions under universal rules. Even the enzymes responsible for replication, transcription, and translation share a high degree of similarity, implying that early life did not reinvent these mechanisms independently on multiple occasions, but inherited them from a common source. This level of conservation hints that the emergence of life was not a series of isolated events, but rather a singular, shared beginning, potentially seeded elsewhere in the cosmos and subsequently propagated to Earth. If we consider an extraterrestrial origin for LUCA, the universality of DNA and RNA could be interpreted as a genetic signature left by a life form or civilization that deliberately or naturally spread life. The same genetic language found on Earth could exist on other worlds seeded by similar processes. This would mean that the apparent unity of life on Earth is not merely the result of Earth-bound evolution, but may reflect the inheritance of a pre-existing, organized genetic system. Such a scenario elevates the panspermia hypothesis from the transfer of organic compounds to the actual distribution of living organisms, or proto-life forms, capable of replication and evolution. Molecular studies further support this view. Comparative genomics shows that even the most divergent life forms share core genes involved in essential processes like DNA replication, RNA transcription, protein synthesis, and metabolism. The probability that these systems evolved independently on Earth in exactly the same way is astronomically low, suggesting that the blueprint for life had a single, highly optimized origin. From a panspermia perspective, it is conceivable that this optimized genetic machinery was packaged into hardy microorganisms capable of surviving interplanetary or interstellar journeys, ready to replicate as soon as they arrived in a hospitable environment. Some scientists have even proposed that the very chemical properties of nucleotides and amino acids might make them universal building blocks for life anywhere in the cosmos. If life arises elsewhere, the same nucleotides and amino acids could be favored due to their chemical stability, reactivity, and ability to form functional polymers. In this context, the shared genetic architecture on Earth may not be unique, but rather a manifestation of universal biochemical principles. Yet, if panspermia played a role, it would mean that the universality of life on Earth is a direct result of seeding from a common extraterrestrial source rather than convergent chemical necessity. Further evidence comes from the genetic codes, resilience, and adaptability. DNA and RNA are remarkably robust, capable of storing vast amounts of information and undergoing evolution over billions of years while retaining functional integrity. This robustness would be essential for any life form transported across space, where it would face radiation, desiccation, and extreme temperatures. The very properties that allow Earth life to thrive and evolve may be the same properties that made it capable of surviving the journey from another planet, moon, or star system. In this way, the shared genetic code is not just evidence of common ancestry, it could be evidence of common cosmic ancestry. The implications are profound. If life on Earth shares a genetic blueprint with life elsewhere, it would suggest that biology is not an isolated phenomenon, but a distributed system across the galaxy. Each planet that harbors life could potentially carry organisms with a recognizable genetic signature, a distant echo of the same progenitor that seeded Earth. This possibility also reframes the search for extraterrestrial life. Rather than expecting entirely alien biochemistry, we might find familiar nucleotides and amino acids on other worlds, evidence that life shares a common cosmic lineage. Moreover, the genetic clues raise philosophical questions about the nature of life itself. If all terrestrial organisms inherit a genetic template that may have originated off-world, then humanity's story is part of a broader, interconnected narrative that spans the galaxy. The DNA in our cells could be a direct link to ancient life forms that existed long before Earth formed, carrying with it the history of distant worlds and perhaps even the intentions of the civilization that initiated the seeding, in the case of directed panspermia. Every cell, every organism, would thus be a participant in a story that extends far beyond our planet, a living testament to the possibility that life is a universal phenomenon rather than a planetary accident. Beyond the genetic blueprints preserved in DNA and RNA, the cosmos itself provides evidence that life, or at least the precursors of life, may be far more widespread than previously imagined. One of the most compelling pieces of this puzzle comes from the discovery of complex organic molecules, often referred to as molecular fossils, in interstellar space and within meteorites. These molecular fossils include amino acids, sugars, nucleobases, and other carbon-based compounds fundamental to life. Their existence in space suggests that the chemistry of life is not unique to Earth, but may be universal, supporting the plausibility of panspermia as a mechanism for spreading life across the cosmos. Interstellar clouds, vast regions of gas and dust between stars, have proven to be surprisingly rich in organic chemistry. Observations using radio telescopes and spectroscopic techniques have detected molecules such as formaldehyde, methanol, acetic acid, and even amino acids in these clouds. These compounds are remarkably complex considering the harsh conditions of space, including extreme cold, ultraviolet radiation, and low densities. Yet, chemistry continues, albeit slowly, catalyzed on the surfaces of dust grains or within icy mantles that coat interstellar particles. These molecular processes result in the formation of compounds that are essential for the building blocks of life, effectively creating a cosmic laboratory where prebiotic chemistry occurs naturally on a galactic scale. Meteorites provide a more tangible record of these molecular fossils. Carbonaceous chondrites, a class of meteorites rich in organic material, have yielded dozens of amino acids, sugars, and nucleobases upon careful laboratory analysis. The Murchison meteorite, which fell in Australia in 1969, contained over 70 different amino acids, many of which are rare or absent on Earth. In addition, ribose, the sugar that forms the backbone of RNA, has been detected in meteorite samples, providing direct evidence that the fundamental ingredients for life can exist in space independently of terrestrial processes. These discoveries suggest that the molecules required for life are not confined to planetary surfaces, but are widespread throughout the cosmos, ready to participate in the emergence of life wherever conditions allow. Molecular fossils in space also support the notion that life could survive transport across interstellar distances. While complex molecules are more fragile than robust microorganisms, their survival in comets, meteoroids, or icy dust particles indicates that they can endure prolonged exposure to cosmic radiation and the vacuum of space. As such, these molecules could be delivered intact to young planets via natural processes, seeding them with the precursors necessary for life to develop. In a sense, these molecular fossils act as cosmic templates, predisposing planets to the emergence of life once environmental conditions become suitable. The detection of prebiotic molecules in both interstellar clouds and meteorites also implies that the chemistry necessary for life may be universal. If amino acids, sugars, and nucleobases are forming naturally throughout the galaxy, then the emergence of life may not be a rare accident, but a likely outcome wherever these molecular building blocks converge in favorable conditions. Panspermia, in this context, becomes not merely a hypothesis about the transfer of life, but a reflection of a universe in which the seeds of life are continuously created, dispersed, and ready to sprout on suitable worlds. Additionally, molecular fossils help bridge the gap between chemical evolution and biological evolution. They demonstrate that complex organic chemistry, which underlies the origin of life, is not restricted to earthbound conditions. Instead, the same processes that produce amino acids or nucleobases in interstellar space could have contributed to life's emergence on Earth, either through direct deposition via meteorites and comets, or by catalyzing reactions in the primordial environment. This continuity, from cosmic molecular chemistry to planetary life, supports the panspermia hypothesis by showing that life's essential ingredients are already present and mobile across space. Laboratory simulations further reinforce these findings. When scientists recreate the conditions of interstellar space, low temperatures, high vacuum, exposure to ultraviolet radiation, organic molecules spontaneously form on simulated cosmic dust grains. These experiments show that space is not barren in terms of chemical potential. Rather, it is an active site for the synthesis of life's building blocks. Once formed, these molecules can be preserved in ice or rocky debris and transported across interstellar or interplanetary distances, providing a ready-made toolkit for the emergence of life wherever it lands. Even more intriguingly, some molecular fossils suggest a level of chemical sophistication beyond simple amino acids. Complex chains, branching structures, and enantiomeric forms, mirror image molecules, have been detected in meteorites and interstellar dust. These compounds hint at the early organization of chemistry in ways that could predispose it toward the development of living systems. In this sense, molecular fossils are not merely passive remnants. They are active participants in the cosmic story of life, carrying information, potential, and continuity from the interstellar medium to the surfaces of planets. Ultimately, molecular fossils in space provide a powerful piece of the panspermia puzzle. They demonstrate that the universe is naturally endowed with the chemical machinery for life, that these molecules can endure extreme environments, and that they can be delivered to planets in forms ready to participate in the emergence of biology. Whether life arrived on Earth via natural panspermia, directed panspermia, or a combination of both, the widespread presence of these molecules shows that the seeds of life are everywhere, scattered across the cosmos and waiting for the right conditions to flourish. By studying molecular fossils, we gain not only chemical insights, but also a profound perspective on life's potential universality, reinforcing the notion that Earth may be just one node in a vast, interconnected network of biologically relevant matter. Despite the fascinating evidence supporting panspermia, the hypothesis is not without its critics, and scientific skepticism remains robust. One of the central criticisms stems from the fundamental lack of direct proof that life, or even viable microorganisms, has traveled from one celestial body to another. While meteorites, comets, and interstellar dust carry organic compounds and molecular fossils, no unequivocal evidence has yet been found that life itself exists beyond Earth or that it successfully arrived here from another location. Without such direct confirmation, panspermia remains a compelling but unproven theory, offering possibilities rather than certainties. Skeptics also point out that even if organic molecules can survive the harsh conditions of space, the transition from complex chemistry to living organisms is far from trivial. The origin of life, even in laboratory simulations on Earth, requires a precise combination of chemical reactions under specific conditions. The leap from amino acids, sugars, and nucleobases to self-replicating, metabolically active cells is immense, and there is no experimental evidence demonstrating that life can spontaneously assemble in space. Critics argue that while panspermia may explain the distribution of life's building blocks, it does not answer the deeper question of life's actual origin: where, when, and how the first living system emerged. Another point of contention involves the survival of microorganisms during interstellar travel. While extremophiles on Earth demonstrate remarkable resilience, critics note that the timescales involved in interstellar journeys are vast, potentially millions to billions of years. Cosmic radiation, extreme temperatures, and prolonged exposure to vacuum are extreme conditions even for the hardiest microbes. The probability that a microorganism could survive intact across such immense distances and times is considered by some scientists to be extremely low. Even for interplanetary panspermia within a solar system, the challenges of surviving high-velocity impacts, re-entry heating, and radiation exposure are non-trivial, raising questions about whether life could realistically endure the journey. The directed panspermia hypothesis, which suggests deliberate seeding of planets by an advanced civilization, also invites skepticism. While intellectually provocative, it introduces numerous uncertainties and assumptions. Critics question the existence, capability, and motives of such a civilization, and there is no empirical evidence to support this scenario. Without tangible proof, directed panspermia can be seen as a form of speculative cosmology, an interesting idea, but one that currently lies outside the bounds of testable science. Moreover, invoking extraterrestrial intervention risks substituting one mystery with another. Even if life were seeded intentionally, the origin of the seeding civilization itself remains unexplained. The lack of identifiable extraterrestrial life is another major criticism. Despite decades of astrobiological research, including missions to Mars, Europa, and other celestial bodies, no living organisms have been definitively discovered beyond Earth. While this absence does not disprove panspermia, it leaves a significant gap in the evidence chain. If life has traveled between planets or star systems, it seems peculiar that no independent traces have been found elsewhere, particularly in nearby environments such as Mars or icy moons, which are considered highly promising for the survival of microbes. Critics argue that until life is detected beyond Earth, panspermia remains a hypothesis grounded largely in circumstantial evidence. Even the meteorite evidence is subject to debate. While amino acids, nucleobases, and molecular fossils have been found in meteorites, contamination from Earth remains a valid concern. Some skeptics suggest that these compounds could have formed or been altered after landing on Earth, calling into question their extraterrestrial origin. Similarly, structures in meteorites that resemble microbial fossils, such as those in the ALH 84001 Martian meteorite, remain highly controversial. Many scientists argue that abiotic processes can produce similar morphologies, meaning that these structures cannot be confidently interpreted as evidence of extraterrestrial life. Criticism also arises from philosophical and methodological considerations. Some scientists argue that panspermia, while plausible, simply relocates the question of life's origin rather than answering it. Even if life arrived from Mars, interstellar space, or a directed seeding, the question remains: where did the first life arise, and how? In this sense, panspermia is often viewed as a partial explanation, a mechanism for distribution, not a solution to the fundamental enigma of abiogenesis. Skeptics emphasize that without evidence for life elsewhere, the theory risks being more of an elegant speculation than a testable scientific framework. Moreover, statistical considerations raise further doubts. The likelihood of survival during transport, successful delivery to a habitable environment, and subsequent proliferation is influenced by numerous low-probability events. While the vast number of potential carriers across astronomical timescales increases the odds, critics argue that the combination of challenges may render interstellar panspermia exceedingly improbable. Even interplanetary panspermia, though more feasible, faces similar probabilistic hurdles, prompting some to view natural panspermia as an interesting idea rather than an established fact. Despite these critiques, it is worth noting that skepticism does not equate to dismissal. Panspermia remains a scientifically grounded hypothesis supported by indirect evidence and consistent with observations of organic molecules, extremophiles, and planetary chemistry. It highlights the possibility that life is not strictly earthbound, opening avenues for research in astrobiology, planetary science, and molecular biology. However, until direct evidence, such as viable extraterrestrial microbes or unambiguous biosignatures, is discovered, panspermia will continue to occupy a space between plausible theory and speculative science. The philosophical implications of panspermia are as profound as they are far-reaching, challenging humanity's perception of its place in the cosmos and reshaping our understanding of life itself. If life did not originate exclusively on Earth, but instead arrived here from another celestial body, or even from another star system, it forces a radical reconsideration of the human narrative. Rather than being an isolated, self-contained phenomenon, life on Earth could be seen as part of a broader interstellar continuum, a biological thread woven into the fabric of the cosmos. The very notion that our existence might be linked to events and environments far beyond this planet invites questions that transcend traditional science, merging empirical inquiry with philosophy and ethics. At the heart of this perspective is the recognition that humanity may be part of a universal family of life. If microorganisms, organic molecules, or even directed life-seeding strategies have spread across the galaxy, then other planets, whether in our solar system, have been seeded with life system or in distant exoplanetary systems, could harbor life that shares a common ancestry with terrestrial organisms. This interconnectedness implies that all life on Earth, from the simplest bacterium to the most complex human, carries a story that begins not just on our planet, but across the stars. Humanity, then, is not an isolated outgrowth of local chemistry, but a participant in a grander cosmic narrative, linked to a lineage that may span multiple worlds and eons of interstellar travel. This universality challenges anthropocentric views of life, suggesting that our species is one node in an expansive, interconnected web that stretches across the galaxy. Such a cosmic perspective profoundly impacts how we view evolution. Traditional Darwinian evolution is framed within the context of Earth's biosphere, shaped by environmental pressures and random mutations over billions of years. Panspermia, particularly if it involves interplanetary or interstellar transfer, suggests that the starting conditions for life on Earth may have been influenced by external, potentially extraterrestrial factors. Life here could be the continuation of a much longer evolutionary process that began on another world, implying that the history of life is not confined to this planet, but may have cosmic roots. In this sense, evolution is no longer a purely terrestrial story. It is part of a universal continuum in which life adapts, survives, and propagates across environments that span planetary systems and perhaps entire galaxies. Philosophically, this perspective also reshapes our understanding of humanity's uniqueness and responsibility. If life is a cosmic phenomenon, humans are not merely earthbound creatures, but representatives of a broader biological heritage. This realization carries ethical implications. If we are part of a universal biosphere, our actions on Earth acquire greater significance. Our stewardship of the planet, our impact on other life forms, and even the potential contamination of other worlds during space exploration must be considered not merely in local terms, but as part of our role in the preservation or disruption of life at a cosmic scale. Humanity may, in effect, be both a beneficiary and a custodian of a biological legacy that transcends planetary boundaries. The idea of cosmic life also invites profound questions about identity and belonging. In traditional human thought, our origins are tied intimately to Earth, to specific ecosystems, and to ancestral lineages traced through millennia of evolution. Panspermia expands this frame dramatically, suggesting that the molecular building blocks of life, or even the first living organisms, may have existed before Earth itself formed. If so, every living cell on Earth carries a heritage that predates our planet, connecting us to a history written across the cosmos. This view transforms existential questions about who we are and where we come from, infusing our understanding of life with a sense of deep temporal and spatial continuity. Humans may be seen as cosmic citizens, participants in a universal biological enterprise that began in the cold reaches of space long before our Sun and Earth came into existence. Moreover, if directed panspermia is part of the equation, philosophical questions about intention, design, and purpose enter the discussion. The possibility that life on Earth was intentionally seeded by an advanced civilization invites speculation about the motives behind such an act. Was it a gesture of benevolence, a form of scientific experimentation, or an attempt at cosmic legacy? If life was deliberately spread, then our very existence might carry embedded meaning, not as a random accident, but as the product of a conscious act with intent spanning cosmic distances and millennia. This reframing touches on questions traditionally reserved for theology and metaphysics. Are we the beneficiaries of a deliberate cosmic plan, and if so, what responsibilities accompany such a legacy? Panspermia also impacts our understanding of death, life cycles, and continuity. In a universe where life is potentially widespread and continuously propagated, mortality takes on a different dimension. The extinction of a species, while tragic locally, may be part of a larger cycle in which life persists elsewhere, adapts to new environments, and spreads across time and space. Humanity's biological imprint could continue in ways we do not yet perceive, through the survival of microorganisms, engineered organisms, or even life's remnants carried into space by our technological activities. In this sense, life transcends individual species, planets, and even human comprehension, existing as a persistent, evolving phenomenon in the cosmos. The possibility of cosmic life also carries profound implications for our search for meaning and purpose. If life is not a rare accident, but a universal phenomenon, then our understanding of existence must extend beyond anthropocentric or planet-centric frameworks. Life may be a fundamental property of the universe, an emergent phenomenon that occurs wherever conditions permit, and humanity may be one expression of a far larger, distributed system of biological organization. This perspective encourages a sense of humility and awe, highlighting that the emergence of consciousness, intelligence, and culture on Earth is not an isolated miracle, but part of a broader tapestry of life, unfolding across space and time. Furthermore, the notion of a universal family of life reshapes how we consider interstellar exploration and contact with extraterrestrial biology. If life is cosmic in origin, then discovering life elsewhere, even microbial, would not be an isolated curiosity, but a confirmation of a shared heritage. Communication or interaction with such life, whether microbial or intelligent, could reveal profound truths about the continuity, adaptability, and distribution of life across the cosmos. It could redefine our place in the universe, turning the act of exploration into a dialogue with distant kin, connected by evolutionary and chemical threads that traverse light years. The philosophical implications of cosmic life challenge the boundaries between science, imagination, and existential inquiry. Panspermia is not merely a scientific hypothesis. It is a lens through which to view the universe and our place within it. By suggesting that life is not earthbound but universal, it bridges the gap between empirical discovery and the profound human need to situate ourselves in a larger context. It fosters a sense of belonging that transcends planetary borders, a recognition that every organism, every ecosystem, and every human being may be part of a story written on a cosmic scale, a story that stretches across planets, stars, and millennia, connecting the living fabric of the universe in ways we are only beginning to understand. Contemplating humanity's place in a cosmos teeming with life, even at the microbial level, expands our ethical, existential, and philosophical horizons. We are no longer simply Earth dwellers. We may be participants in a vast, interconnected, and ongoing experiment of life itself. Every heartbeat, every cell division, and every act of human creativity and discovery may be viewed as part of a much larger cosmic continuum. The universe, in this perspective, is not a lifeless expanse of stars and vacuum, but a nurturing environment in which life emerges, evolves, and spreads, making humanity both a beneficiary and a steward of a grander universal biological heritage. The panspermia hypothesis naturally extends to the ongoing search for extraterrestrial life, providing a framework that makes the hunt for microbes on other planets and moons not only plausible but profoundly consequential. If life can survive interplanetary or even interstellar travel, then worlds within our own solar system may harbour organisms that share a common ancestry with Earth's biosphere, or, at the very least, contain the building blocks necessary for life to emerge. Mars, Europa, Enceladus, Titan, and other celestial bodies have therefore become prime targets for astrobiologists seeking to test the boundaries of panspermia, as they offer environments that could sustain microbial life. Mars has long captivated scientists because of its proximity, geological history, and evidence that liquid water once flowed across its surface. Ancient riverbeds, mineral deposits, and polar ice caps indicate that the planet may have been habitable billions of years ago, overlapping with the time Earth first saw the emergence of life. The possibility that life on Earth could have originated from Mars, or vice versa, is bolstered by the exchange of meteorites between the two planets. Known Martian meteorites, ejected by asteroid impacts and later landing on Earth, provide a tangible mechanism for the transfer of microbial life. If future missions discover fossilized microbes, living organisms, or biochemical signatures on Mars that resemble Earth life, It would be a strong indication that panspermia played a role in shaping the biospheres of both worlds. Beyond Mars, the icy moons of the outer solar system present equally compelling opportunities. Europa, one of Jupiter's largest moons, is believed to harbour a subsurface ocean beneath its icy crust. Tidal forces generated by Jupiter's gravity create heat within Europa's interior, potentially allowing liquid water to persist and support life. Enceladus, a small moon of Saturn, similarly exhibits geysers that spew water vapour, organic compounds, and salts from its subsurface ocean into space. The presence of these materials, combined with the protective ice shell, makes Enceladus an excellent candidate for harbouring life, or for serving as a conduit for life delivered from elsewhere via panspermia. Missions such as NASA's Europa Clipper and potential future probes to Enceladus aim to analyze the chemical composition of these oceans and plumes, searching for amino acids, nucleotides, or even microbial cells that could provide evidence of extraterrestrial life. Titan, Saturn's largest moon, presents a different but equally fascinating scenario. With its thick, nitrogen-rich atmosphere, methane lakes, and complex organic chemistry, Titan represents a world in which life, if it exists, could be radically different from terrestrial biology. Or it could share common molecular precursors, such as amino acids and simple organic molecules. The study of Titan not only informs the possibility of independent abiogenesis, but also sheds light on how organic compounds, potentially seeded via panspermia, interact with planetary environments to give rise to life. Even comets and asteroids, which have long been considered the vehicles of panspermia, are themselves targets for exploration. Missions like ESA's Rosetta, which studied comet 67P/Churyumov-Gerasimenko, and NASA's OSIRIS-REX, which sampled asteroid Bennu, provide insight into the composition of these celestial bodies. Organic molecules, water ice, and amino acids found on comets and asteroids support the idea that these small bodies can act as carriers of life's building blocks. By studying them in detail, scientists hope to understand whether microbial life or complex prebiotic molecules could survive the extreme conditions of space and be delivered intact to habitable environments like early Earth or Mars. The discovery of extremophiles on Earth further strengthens the case for searching for extraterrestrial microbes. Organisms that thrive in extreme heat, cold, radiation, or high salinity demonstrate that life can persist in environments once thought inhospitable. If Earth life can survive conditions analogous to those on Mars, Europa, or Enceladus, it is plausible that similar microorganisms could exist on these worlds. This realization directly ties into panspermia, suggesting that if microbes can endure interplanetary journeys, then they could also colonize distant planets and moons, creating a biological network across the solar system. Search strategies now often integrate cutting-edge technology, from robotic landers and orbiters to spectroscopy and remote sensing. Instruments capable of detecting biosignatures, such as methane plumes, isotopic ratios indicative of biological processes, or the presence of complex organic molecules, are central to these efforts. Future missions may include subsurface drilling to reach protected habitats, cryogenic sampling to preserve potential microbial life, and in situ analysis of chemical compounds in order to detect life that could have been transported via natural or directed panspermia. Importantly, the search for extraterrestrial microbes does not only test the plausibility of life surviving interplanetary transfer, it also probes the potential universality of life itself. Finding organisms with biochemistry similar to Earth life would support the idea that life can be distributed via panspermia, whereas discovering life with entirely distinct chemical pathways could indicate that life can arise independently, suggesting that the universe is even more fertile biologically than previously imagined. Both outcomes would revolutionize our understanding of biology, cosmology, and the interconnectedness of life. Furthermore, detecting extraterrestrial microbes carries implications for planetary protection and ethics. If life exists beyond Earth, even in microscopic form, humans must carefully consider contamination risks. Sending probes, landing spacecraft, or returning samples must be conducted under stringent protocols to avoid inadvertently seeding or destroying alien ecosystems. This necessity aligns with the broader philosophical implications of panspermia. Life may be a shared cosmic heritage, and humanity has a responsibility to preserve, protect, and study it with humility. Ultimately, the hunt for extraterrestrial microbes links directly to the central questions posed by panspermia. Are life's origins local or cosmic? Did microorganisms hitch a ride on meteorites or comets to seed multiple worlds? Are we alone, or is Earth simply one node in a larger network of life scattered across the solar system? Each mission to Mars, Europa, Enceladus, or Titan brings us closer to answering these questions, potentially confirming that life is not an isolated phenomenon, but part of a universal tapestry extending far beyond our planet. In doing so, these searchers do more than seek aliens. They test the very idea that life is a cosmic phenomenon, validating or challenging one of the most profound scientific and philosophical hypotheses in human history. Looking to the future, the verification of panspermia will depend not just on theoretical modeling or indirect evidence, but on concrete experiments and missions designed to directly sample extraterrestrial materials and environments. Several ambitious projects currently in development aim to bring us closer to understanding whether life, or at least its molecular precursors, can be distributed across space, potentially confirming that the seeds of life have traveled from one world to another. These missions will explore asteroids, comets, moons, and even interstellar objects, providing unprecedented insight into the chemistry and biology of the cosmos. One of the most critical areas of focus is the sampling of asteroids. Asteroids, particularly carbon-rich bodies, are thought to contain organic molecules and possibly microbial life or their precursors. NASA's OSIRIS-REX mission, which returned samples from asteroid Bennu, is a prime example. The meticulous analysis of these samples on Earth allows scientists to study the presence of amino acids, nucleobases, and other complex organic compounds that could provide evidence for natural panspermia. Similarly, Japan's Hayabusa 2 mission, which returned material from asteroid Ryugu, has provided additional samples rich in organic molecules. Future missions building on these successes aim to examine these asteroidal materials more deeply, searching for isotopic ratios, molecular structures, and microfossil evidence that could indicate that asteroids act as natural delivery vehicles for life. Comets, long considered cosmic messengers due to their high organic content and icy composition, are also key targets. The European Space Agency's Comet Interceptor mission, set to launch in the mid-2020s, plans to rendezvous with a long-period comet or interstellar object that has never before entered the inner solar system. This mission will provide a rare opportunity to study pristine cometary material, potentially containing organic molecules that predate the solar system. The analysis of water ice, organic-rich dust, and volatile compounds within these comets could provide strong evidence that comets serve as delivery vessels for life's building blocks, reinforcing the natural panspermia hypothesis. By sampling comets that have remained largely unchanged since the solar system's formation, scientists hope to gain insight into the availability and survival of prebiotic molecules in space. Planetary moons, particularly those with subsurface oceans, are another crucial arena for panspermia experiments. Europa, with its global ocean beneath an icy crust, is slated for exploration by NASA's Europa Clipper mission. Equipped with ice-penetrating radar, spectrometers, and particle analyzers, the Clipper will examine the Moon's surface and plumes for signs of organic molecules, salts, and other biosignatures. If life exists, or has existed, in Europa's ocean, it could provide a living record of biological transfer processes within our solar system. Enceladus, with its geysers ejecting water and organic compounds, remains a top candidate for future lander missions, which could capture plume particles directly, searching for microbial cells, isotopic anomalies, or complex molecules that might indicate an extraterrestrial origin for life. In addition to these targeted missions, scientists are also planning laboratory experiments and simulation studies to complement observational efforts. For example, simulated interstellar travel experiments subject microorganisms to vacuum, cosmic radiation, and extreme temperature fluctuations to determine whether life could survive the journey from one planetary system to another. These studies, combined with spaceflight experiments aboard the International Space Station, where microorganisms are exposed to real space conditions, help validate the viability of both natural and directed panspermia mechanisms. If microorganisms or spores can endure these conditions for extended periods, the likelihood of panspermia increases significantly. Future missions may also take advantage of sample return techniques from distant moons and comets. Unlike simple remote sensing, physically bringing extraterrestrial material to Earth allows for far more detailed and sensitive analyses, including DNA/RNA analogues, isotopic ratios, and molecular chirality studies. The ability to conduct high-precision tests in Earth laboratories increases the chances of detecting subtle biosignatures that could otherwise be missed by instruments in space. These techniques could eventually answer whether life's building blocks have a universal distribution, and whether life itself might have traveled between worlds. Even interstellar objects like Oumuamua, which briefly passed through our solar system, are now considered potential carriers of life. Although fleeting, their observation and potential future interception could provide direct evidence of life's interstellar dispersal. Proposed missions aim to rendezvous with such objects, sampling material that has traveled for millions or even billions of years across the galaxy. If these objects contain complex organics or even preserved microorganisms, it would represent a breakthrough for the panspermia hypothesis, demonstrating that life's reach is not limited to our solar system. In addition to hardware missions, future experiments are incorporating advanced computational modeling. Simulations of impact ejector, cometary trajectories, and interstellar dust dynamics help predict how life could travel between planets or star systems. These models, when combined with actual sample analysis, provide a comprehensive picture of how panspermia could occur naturally, identifying the most likely paths and survival rates for life across vast distances. They also help refine mission targets, focusing efforts on the celestial bodies and materials most likely to yield evidence for life's transfer. The integration of multidisciplinary approaches is central to testing panspermia. Astrobiology, planetary geology, chemistry, molecular biology, and computational physics converge to create a comprehensive investigative framework. Each mission and experiment, whether it examines a meteorite's amino acids, a comet's ice composition, or a subsurface ocean's potential microbes, contributes a piece of the larger puzzle. The ultimate goal is not only to confirm the plausibility of life traveling through space, but also to trace its pathways, determine its survivability, and perhaps even identify whether Earth's life shares a common ancestry with organisms elsewhere. Ultimately, these future experiments could transform our understanding of life's place in the cosmos. Success would validate panspermia as a mechanism for spreading life, bridging the gap between molecular fossils in space and living organisms on Earth. We might find that life is a ubiquitous cosmic phenomenon, a natural consequence of chemistry and physics rather than a singular terrestrial accident. Each new discovery, whether confirming or challenging aspects of the hypothesis, will expand the horizons of science and philosophy alike, reshaping humanity's perception of its role in the universe. As we step back and reflect on the vast expanse of the cosmos, the panspermia hypothesis invites us to reconsider the very essence of life on Earth. The possibility that life's origin is not confined to our planet, but instead stretches across planets, moons, comets, and perhaps even star systems, reshapes the story of existence. Every living organism, from the simplest bacterium in a deep-sea vent to the towering redwoods of ancient forests, may carry within it a heritage that predates Earth itself. This idea elevates life from a purely terrestrial phenomenon to a cosmic narrative, suggesting that Earth is not the cradle of life, but a recipient of a much grander, universal process. The implications are staggering. Life may be a shared legacy, a network of organisms connected not only by DNA and RNA, but by the very matter and molecules that have traversed space for eons. The awe-inspiring reach of panspermia becomes clearer when we consider the resilience of life itself. Extremophiles on Earth have demonstrated the extraordinary capacity of organisms to survive under conditions once thought inimical to life. Searing heat, intense radiation, crushing pressure, and the vacuum of space. Microbes buried in rock or ice, surviving millennia in dormant states, underscore the plausibility that life could endure interplanetary travel, perhaps riding on meteors or hitching a ride within comets. Each extremophile is a testament to life's stubborn persistence, revealing that life is not merely an earthbound occurrence, but a phenomenon that can endure, adapt, and traverse cosmic distances. This cosmic perspective also transforms how we perceive our place in the universe. Humans, who have long regarded themselves as the apex of life on Earth, may instead be part of a far-reaching biological continuum. Our bodies, composed of trillions of cells, are built from elements forged in stars, and now, potentially, from microorganisms that originated elsewhere in the cosmos. If life was seeded from Mars, a comet, or an interstellar cloud, then the story of human evolution is intimately tied to events that occurred far beyond our planet. Each heartbeat, each breath, and each living cell is part of a lineage that may stretch across the galaxy, linking Earth's biosphere to distant worlds and ancient stars. The idea is humbling, inspiring, and profoundly unifying, suggesting that all living things are part of a shared cosmic heritage. The philosophical and existential dimensions of this understanding are equally striking. If life is indeed cosmic in origin, it suggests that the universe itself may be inclined toward the emergence of life. Instead of being an improbable accident, life could be a natural outcome of the cosmos, facilitated by chemical processes that occur wherever conditions allow. The implication is that Earth is not unique in fostering life, but is part of a vast galactic network in which life is scattered, evolves, and potentially flourishes on countless worlds. This perspective changes our narrative from one of isolation to one of connection, suggesting that humanity is not alone, that our biosphere is not solitary, and that our story is intertwined with the history of the cosmos itself. Consider the poetic resonance of this idea. Every organism on Earth, from the tiniest virus to the largest whale, carries within it a story written in the stars. The trees that sway in the wind, the oceans teeming with life, the creatures that roam the savannas, all may be descended from cosmic travelers that arrived on our planet billions of years ago. This perspective turns Earth into a stage upon which a universal story unfolds, a chapter in a grander narrative that began long before our planet formed and perhaps continues beyond the boundaries of our solar system. Our very existence may be the product of a chain of events spanning planets, asteroids, and interstellar space, a sequence of miraculous survivals and deliveries that ultimately converged on this blue planet we call home. The search for extraterrestrial life, the study of meteorites, comets, and icy moons, and the exploration of molecular fossils in space are all extensions of this grand inquiry. Each mission, each experiment, and each discovery adds another verse to the cosmic poem, revealing not only the mechanics of life's dispersal, but also its profound significance. The discovery of amino acids on asteroids, the identification of complex organics in interstellar clouds, and the resilience of extremophiles on Earth all point to a universe that is not indifferent but, in a sense, nurturing to life. These discoveries hint that life is not a mere accident on a solitary planet, but a process that is written into the very chemistry of the cosmos. If directed panspermia is also considered, the implications become even more awe-inspiring. The notion that advanced civilizations might have intentionally seeded worlds with life invites the possibility of cosmic stewardship and continuity. Even if we cannot yet prove the existence of such civilizations, the idea challenges us to imagine life as part of an intentional, interstellar narrative. It expands the horizon of human thought, asking us to consider our potential role not only as recipients of life, but perhaps as future contributors to its cosmic propagation. If life is deliberately spread, the ethical and philosophical dimensions of our exploration, colonization, and technological achievements take on new meaning. Humanity may have a role in continuing the chain of life, ensuring its resilience and propagation beyond the confines of our planet. From a scientific perspective, each new discovery strengthens the plausibility of panspermia, while simultaneously deepening the mystery. Life's chemical precursors are found throughout the galaxy, in comets, meteorites, and interstellar clouds, suggesting that the raw ingredients for life are widespread. Extremophiles demonstrate the survival potential necessary for interplanetary or interstellar transfer. Missions to Mars, Europa, Enceladus, and asteroids aim to uncover evidence of past or present life, providing opportunities to test whether life has indeed traveled across space. Together, these lines of evidence converge on a striking possibility: that Earth is not the origin of life, but a hub within a vast interconnected web of biological activity spanning the cosmos. And yet, despite these tantalizing clues, the mystery remains, deep and beautiful in its complexity. Every question answered seems to give rise to more questions. If life came from Mars, did it begin there, or was it already traveling from another star? Are there other planets in the galaxy that harbor life sharing our ancestry, or entirely distinct forms? Could intelligent life elsewhere have played a role in spreading life deliberately? Each of these possibilities stretches our imagination, reminding us that the universe is far vaster, older, and more intricate than we can fully comprehend. Ultimately, the greatest wonder of panspermia is its capacity to transform our perspective on life itself. It teaches humility, urging us to recognize that we are part of something far larger than ourselves. It teaches curiosity, motivating us to explore distant planets, moons, comets, and asteroids in search of life's origins. And it teaches awe, revealing that the simple act of existence, breathing, thinking, growing, and reproducing, is part of a story that spans the galaxy. If panspermia is true, then every tree, animal, and human on Earth is part of a story that began among the stars. Every molecule, cell, and organism carries with it a cosmic history, a lineage that links Earth to the broader universe and connects us all to a shared heritage written not just in DNA, but in the very fabric of the cosmos itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.